So today we're going to go a little bit different direction. Going to get into reading data sheets and calculating the propagation delay of gates and logic. This is a data sheet for a 74HC04 hex inverter, which you use in Digital Logic Lab. Although you probably use the LS version, which is, let me see here, right here. This is the data sheet for it. Gives you the pinout. On the thing, and on the chip, and the different packaging styles, the function table, high in, low out, low in, high out. Familiar with that? Symbols for the thing, and the actual circuit on the inside, how it works. I showed you a one transistor version of the inverter. This version uses 1, 2, 3, 4, 5 different transistors, a diode, and 4 resistors. So well, the LS version that you use uses a bit more, but it's a low power Schottky device. That's what LS stands for, low power Schottky device. But gives you the operating ranges, operating conditions that are recommended. Using 5 volts. What is a low level input voltage? 0.8 volts maximum. How much current can it generate? 16 milliamps. So it can't supply a whole lot of power. Let's see here. Where was I trying to get to the propagation delay? Switching characteristics. The time it takes to go from low to high, 12 nanoseconds. From high to low, 8 nanoseconds. The maximum being 15 and 22. Now, a nanosecond is approximately the time it takes light to travel between my 2 fingers. So it's a very brief amount of time. Electrical signals go at about a rate of, I want to say, 11.2 inches per nanosecond. So if you have a 3-foot long wire, it'll take 3 nanoseconds to get from one end to the other, give or take. When you have lots of gates in a row, you have to, in sequence, in series, you have to add up those propagation delays because they can add up pretty quickly. going back to the original one, that I pulled up, the propagation delay here is 6 nanoseconds. Time PD 6 nanoseconds. So that is significantly faster than the potential for 22 nanosecond delay in the LS version. The HC is a high-speed CMOS. HC stands for high-speed CMOS. So it's a different technology used to manufacture the chip. When I was downloading these, I forgot to look at the difference in prices, but I would imagine the LS is cheaper. It's an older technology. The HC is newer technology and quite a bit faster. I also downloaded the a chip that has two positive edge triggered D-type flip-flops. 1.9 nanoseconds. That's really snappy for digital logic. When you're dealing with processors, a processor that was running at 1 gigahertz, the clock period is 1 nanosecond. So if it's waiting for external logic like this, it might have to wait several clock cycles depending on the external logic, speed of the external logic, for the results to be valid, because things don't happen instantaneously. But this also leads us to a different take on the positive edge trigger D-type flip-flop. Okay, the flip-flop is let's see here. There's the D-type flip-flop is like so. And you have the clock and D here. Okay, and that's the D latch, not the flip-flop. Okay, I showed you last lecture the rather complex positive edge trigger flip-flop. Not expecting you to memorize it or have it in your notes or whatever, but it's 3 SR latches interlinked together. What you could do with the clock here, is have an AND gate with one input inverted. Now we just saw the propagation delay of the inverter as low as 6 nanoseconds. So when a clock pulse comes here, say a clock pulse is this long, the AND gate is going to stay low, okay, because ANDing a value with its inverse keeps it low, it stays at 0, right? But there's a slight delay in the with the inverter, 6 nanoseconds. So while this is low, while the clock is low, this is high here. So it has a high input, one high input to the AND gate. When the clock pulse goes high, there's a delay here, but instant here. So for a short period of time, 6 nanoseconds, the output from the AND gate will be high. That will, and while for that 6 nanoseconds, whatever values on the D line will be propagated through to the latch. And then, so from this is the clock pulse. Here, you're going to see a very short pulse. So while it's not technically a D-type flip-flop, it will work as one. A positive edge trigger D-type flip-flop. So that's just playing with the propagation delays of your various components. But and then whatever goes through here goes through, it goes through during those 6 nanoseconds. So that I'll be honest with you, because this is my first time teaching this class, I didn't know what pace we were to take and what all we were supposed to cover. And it turns out the other class doesn't go as far as we have with this. So I'm at a loss for where to go to next as far as covering different topics and that sort of thing. So the next week will be, I don't know, brief lectures and reviews for the final. So please be present. I will be taking roll, but mainly I want it to be a review of any topics that you guys might be weak on or want to review again, that sort of thing. So we might cover a little bit of new material as I read about it, refresh my memory on it in the textbook that I have. But for the most part, the content for the semester is basically done. Like I said, I might introduce a few new topics as they occur to me or as I remember them, but keep in mind with digital logic, because digital logic is the foundation for computer architecture, anything that can be done in software necessarily can be done in hardware. And when you're dealing with hardware, things happen a lot quicker. So if there's a process that you want to do, a simple process that you want to do very quickly, repetitively, and often, it makes sense to make a logic circuit that will execute that process in hardware instead of in software. I was tasked for another class to put together a schematic of a circuit that would help facilitate encryption. It took a while and had to break things down to a very elemental level, but it was possible. I was able to do most of it in hardware, and it would speed up the encryption process considerably. People have already done it. It's not new technology or anything like that. Various telecommunications devices already include this type of hardware, but I was tasked with creating a schematic to show students and break things down to their, like I said, elemental level. And that's what digital logic does, is breaks things down to the and, or, and not of the of a process. So anyway, I think that's about it for today. Like I said, the remaining lectures will be brief, and put together your questions, ideas, troubles, whatever, for next week. This Friday, I will not be here. I have to go out of town, but I'll be with you in spirit. Have a good day. See you all on Monday.